So, yeah, I'm your instructor, Jared Gavin, again, and I hope that you found my video on section 1.1 helpful. If there was something that I covered and you feel like you need a little bit more explanation, then feel free to email me. Here's my email address: gavinj@uamont.edu. And with this video, we're going to get started on section 1.2. We're still talking about functions and specifically their graphs and some various properties of these functions. Okay, so example 1, we are given a graph of a particular function f of x, but we are not told what the algebraic expression is that represents this function f. Okay, we're only given a graph. And so what we want to do is simply obtain the f of x given the x in this first table. Okay, we just want to complete this table, and we're going to do our best and try to get as accurate an f of x as we can. Okay, but without the actual algebraic expression, we're going to have to sort of estimate in some cases. Okay, x, our input, in this case, f is a function, and so we could refer to the first column as some of the elements in the domain. Alright, our first value of x is negative 1.5, and so what we want to calculate in this table, and maybe I shouldn't say calculate, we want to find f of negative 1.5, and so the only means by which we do that is this graph here. So I go over here, and the horizontal axis is my x-axis, and this is where I locate the number negative 1.5, and of course the vertical axis is my y-axis. This is where I'm going to read the value for my f of x for whatever the particular x value is. So negative 1.5, we are located to the left of the origin, and I see that each unit, 1, 2, 3, 4, 5, each unit is 0.2. Okay, 1.5 would be located here, right between negative 1.5 and negative 2. So here is x equals negative 1.5. Alright, at this point we simply draw a vertical line up to our f of x, and then once we hit the line, we break perfectly horizontal toward the y-axis, and we try to keep it as straight as we can and horizontal so that we can get an accurate read of what the y value is. So if I look at this on the y-axis, I have 1, 2, 3, 4, 5 units. Okay, a different scale for the y-axis. 5 units represents 2. Okay, 2 divided by 5 would be 0.4, and so I am approximately 1, 2, 3 units up from the origin. So with a value of negative 1.5 for x, I read a value of 3 times 0.4, 1.2 for y. Okay, and this is the procedure that we follow with the rest of these x values. If we go over here to x equals 0, which is the origin, x equals 0, then we see that our function f of x is below the origin, and if we simply track our way down and read the y value, we see that we land about halfway between 0 and -2. So I'm going to call that value a -1. Okay, we could also refer to this -1 as our f of 0, or the value of the function f located at x equals 0. Okay, our next value for x is 1. I go over here and I look on my x-axis, and the function pretty much crosses the x-axis at x equal 1, which is located right here. Alright, since our function itself lies on the x-axis, then our y-coordinate of this point must be 0. Okay, the location of the x-axis with respect to the y-axis is 0, so simply fill in my table with a 0 in the f of x column. And so what we just found can be referred to as f of 1. What about f of 2? Okay, here is 2 on the x-axis. I trace my way vertical until I get to f of x. And then I simply break horizontally towards the y-axis. Okay, and to me it looks like I landed right between 0 and 2, which would be 1 in this case. So f of 2 I'm going to call 1. If you look back, we may have could have called f of -1.5. It landed approximately in the same area, but I called it 1.2. I guess some of that's up to your eye and personal interpretation. What about our next x value, x equals 3? Here is 3 on the x-axis. Draw as a vertical line as I can, and I hit my f function, and now I track my way over horizontally to the y-axis, and to me it looks like I hit 2, and so I would say f of 3, or the y value of f located at x equals 3 is 2. And now my last value of x, 4. Here is x equals 4. Okay. Trace my way vertically to my function, and now horizontally over to the y-axis as best I can. It looks like I hit about halfway between 2 and 4, so I will just simply call that 3. Okay. At the bottom of this page, we have some information about what's called the vertical line test. More than likely, if you took intermediate algebra, you've seen everything that we've done on this page so far, and you've more than likely seen the vertical line test. But what the vertical line test is simply a simple way, if given the graph of a function, or in this case I suppose I should say relation, if given the graph of a particular relation, we can test as to whether it's a function or not. Okay, and the vertical line simply applies to a certain domain, a certain value of the domain. And if you'll remember the definition of a function, we said that each element of the domain can only have 2 outputs. Okay, so in this case, if we draw a vertical line at a particular value of domain, in this case our domain is the x-axis again, and here in this picture we're looking at a domain value, arbitrary. They don't tell us a specific number. They just say a. So if we draw the vertical line, and you see that this vertical line hits 2 points on the graph of this relation, that means that for this one input we have two outputs, y1 and y2. That violates the definition of a function, and so this particular graph does not represent a function. Okay, once again, vertical line test is just a simple way of analyzing a particular graph to see whether it's a function or not. If we draw this vertical line test at any point along the x-axis and we hit 2 or more points on that particular graph, or graph of the relation you could say, then it is not a function. Okay, moving on to the next page. We simply have some examples of some graphs that we're going to apply the vertical line test to and decide whether they are functions or not. Okay, the first one. We can draw our vertical line anywhere along the x-axis. Okay, we could draw it here, but obviously we don't hit the function or the graph of the relation at all. Okay, and we don't hit it over here. It's not located in these areas of the x-axis. These two vertical lines really don't tell us whether this is a function one way or another. Okay, we don't hit the function at all. We are looking for a vertical line that will hit the graph in 2 or more places. Okay, so for instance, if I draw a vertical line here, okay, and by the look of it, I'm somewhere around, let me say, 0.4, or x equals 0.4. You can obviously see that I've hit the graph of this relation multiple times. Therefore, this is not a function. And this only has to happen at one place along the x-axis. Of course, I could go to the opposite side of the y-axis, and here we go. There's another instance of a vertical line that strikes the graph of this relation several times. Okay, and we only have to hit it twice to violate the definition of a function. Okay, this next one, once again, if you took intermediate algebra, you should recognize this as a rational function, and hopefully you remember that rational functions usually have, especially when you see characteristics such as these two vertical lines, okay, and it's important to realize that these two vertical lines are not actually a part of the relation. In this case, they are actually vertical asymptotes. Okay, VA, vertical asymptotes. That may have a P in it. I can't remember right now. But these aren't actually parts of the relation. Okay, and so these are more or less boundaries for the graph of this function, and I'm sort of already giving it away that this is a function. So in other words, if I apply the vertical line test anywhere along the x-axis, you're going to find that I only hit the function once at each instance of x. Okay. Now, The questionable part of this function would be as we get closer and closer to these vertical asymptotes. Let me just simply say that as x gets closer to these vertical asymptotes, we actually shift over, okay, by a small amount, and every little small amount of change in x as it gets closer to, let's see, this particular asymptote looks like it is located at x equal 1, and this other one looks like it's located at x equal 3. So as we get closer and closer to 1, the y value drastically changes. And so that causes us to have a very steep curve, which looks like it may, a vertical line may strike this function twice, but it just doesn't. Okay, so be careful there. In some cases, you just simply have to be familiar with certain algebraic functions. Okay, the next one. We have a spiral, and this is obviously not a function. Okay, there's several places where I could draw a vertical line and hit the spiral twice. If I draw a vertical line pretty close to the y-axis, you can see that I hit it 4 times. Okay. Perhaps over here on the very edge, if I was very precise and accurate about how I drew my vertical line, I could probably position it to where I only hit the spiral once. Okay. But we have these other instances where they don't hit once, they hit several times, and so not a function. Okay. The next one. Okay, this one here. We're just sort of coming in somewhat shallow, and then we pass the y-axis and we start to get steeper and steeper. But judging by what we see here, if we test it with the vertical line test, okay, we see that the function doesn't wrap back around on top of itself. Okay, it doesn't overlap. And so according to the vertical line test and what we can see of this particular graph, this is a function. Okay, there are no places along the x-axis where we draw a vertical line and hit this function more than once. So this is a function. Okay, the next one, again, we have some very steep areas of this particular curve. But if we could draw our vertical lines very vertical and precise, then we would actually only hit this curve once in these areas on the far left and the far right. And then you can probably see more easily that in the middle the same is true. Any vertical line along the x-axis only hits it one time. So this is a function. Okay, this one, not a function. Again, we could probably draw a vertical line here on the side and only strike this curve once, but in the middle. That's not the case. all through the middle, in between the far left and the far right, we're going to hit this curve twice. So this is not a function. So this is really just more of a visual inspection of a particular curve. Let's see if I can move. Oh, I need to erase everything. And here we are with the last two curves. Here we have what looks like an infinity symbol, okay, centered at the origin. And here is one location, and that's all I need to find. One location along the x-axis to where I draw a vertical line and I hit the curve 2 times or more. I can label this one as not a function. And then over here again we see a steep piece of the curve on the far left. It's just simply that. It's very steep, and if we were to draw an accurate vertical line in this area, we would actually only hit it once. Okay, so it's not like this one, infinity symbol. It doesn't wrap back around on itself, and it's not like the circle. It doesn't loop around. Okay, it's a smooth curve that continues to the right and the left indefinitely. Okay, so just based off of what we see, we can pick several other locations along the x-axis. Drawing vertical lines. Here I sort of hit the top of one of the curves, and I only hit it once. No matter where I draw a vertical line, I only hit it once. And once again, the only questionable place is here, and that's just simply because this part of the curve is very steep. But this is an example of a function. Okay, so page 11, example 3, we are now given algebraic expressions, and we're given a place to create a table of values for input and output. And what we're going to do is we're simply going to use those input-output pairs to try to graph a picture of these functions. Okay, and I say function because the instructions tell us that these are functions. Hopefully this first one, f of x equals 3x minus 1, you recognize that as being a linear function because it fits this format. Okay, sometimes you can say a. I like to use the form y equals mx plus b. Just because it was introduced this way in intro algebra. M would be the slope, how much the line is slanted, and b would simply be the y coordinate of the location where this particular line crosses the y-axis. Okay, so this y equals mx plus b format we just simply refer to as the slope-intercept form. M is the slope coefficient of the x term, and b is the y-intercept coordinate. Okay, so whenever you're graphing any type of algebraic equation, it's a good idea, if you aren't familiar with the function, to pick several values of x, and you usually want to pick some negative values and some positive. Okay, so I'm just simply going to pick -2, -1, 0, 1. Okay, it's not really that many, but I'm already familiar with this type of function. It fits this format, so it's linear. Okay, so at this point, for x equal -2, I want to calculate f of -2. And this is just simply telling me to take this expression, 3x minus 1, and plug in -2 in the place of x. Okay. Now we just simply follow the order of operations. Not a lot to do here. 3 times -2 is -6 minus 1. We would get -7, and so we would place that here under the -2. And I would just simply follow this procedure for the rest of my x values that I chose. F of -1, plug it into my expression in the place of x. 3 times -1 is -3, and now I subtract 1 and I get a -4. Zero is always a great number to pick because it'll cancel a lot of the terms out that have a variable in them. And by cancel out, I simply mean when we plug in this 0 and it multiplies the 3, we simply get 0. And so I end up with 0 minus 1 equals -1. Okay, so let me go up here and fill out my table with some of these values of f of x. Okay, -1, I calculated that, and I got -4 for y. I plugged in 0, and I got a -1. Okay, and my last value, f of 1, replace the x with 1. 1 times 3 is 3. I subtract 1 and I get 2. So I'll place the 2 under the 1 in my table. Okay, now I just simply take these pairs of numbers and plot them on my coordinate plane over here to the right. So -2 and -7. Okay. Here's my origin. That means x equals 0, y equals 0. I want to start with my x, and with a value of -2, that means I need to move over 1, 2 to the left. Wherever this coordinate x equals -2 intersects with the y coordinate -7, and I'm simply going to use a scale of 1 for each unit. I need to go down 1, 2, 3, 4, 5, 6, 7. Okay, let me double check that. Okay, that looks right. -2 for x, -7 for y. Where those two coordinates intersect, I simply plot a point. Okay, I'm going to clean my graph up a little bit. Up, erased my point. It was somewhere around there. And now I'll just simply do that with each of the input-output pairs that I have left. -1. Okay, so I go over 1 along my x-axis, draw a vertical dotted line at that location, and now I read my y coordinate -4. I count down from the origin 1, 2, 3, 4, and I'll draw a dotted horizontal line there. Wherever those two dotted lines cross, that's where I would put or plot a point. The next one is 0, so I start at the origin and I stay there. I don't shift left or right, and my y coordinate's -1, so I simply just go down 1 on the y-axis and plot a point. And at this point you're starting to see that all of these points fall along a straight line. And just for completeness, I'll plot this last one, x equals 1. Mean I would shoot over 1 to the right from the origin. And then my corresponding y value is 2, 1, 2 on the y-axis. Those two coordinates intersect around about there. I plotted all my points, and so I just simply connect the dots at this point best I can. Okay, and like I mentioned before, this is an example of a linear function. Okay, I'm going to move the page down, so I have to erase all of this stuff. For A, I'll move it down. And now for B, I've got a new function. It's labeled g of x. And you see that I have this term that has a power of 2. I have an x squared term. Okay, and that 2 is the highest exponent that I have for the x variable in this expression. And so you should recognize this as a parabola. You can also refer to this expression as being quadratic. Okay, simply that it's a polynomial and its highest exponent, its degree, I could say, is 2. Okay, so as in the last example, we pick some negative numbers for x. Always love to throw in 0. It's usually a pretty easy one, easy output to calculate. And I will pick some positive values. Okay, and if you did remember that this is a parabola, then you probably know that it's going to be curved, and that's the case with any polynomial that has a higher exponent than 1. Okay, in this case we have 2, and so when we graph this, it's going to have a curve to it. So let me calculate all of these outputs. I want to calculate g of -2, g of -1, g of 0, and so forth. So I've got my work cut out for me. X is squared, so I simply square my input, which is -2. Then that is followed by -2 times x. I replace the x with another -2. And now I complete that with -3. Okay, so -2 squared would be 4. -2 times -2, I have a +4, and then -3. 4 plus 4 is 8 minus 3, I get 5. G of -1, I square my -1, multiply it by a -2, subtract 3. Okay, I'm just simply following the instructions of this expression, x squared minus 2x minus 3. Okay, -1 squared is a +1. -2 and a -1 multiplied gives me a +2. I subtract 3, and I get a 0. Okay, this next one I actually take 0 and put it into my function. Zero squared 0, negative 2 times 0 is 0, and so inputting 0 sort of knocks out this x squared and negative 2x term. Like I said, it's pretty easy to calculate. I get an output of negative 3. And now I have to calculate g of 1. So I have a 1 squared minus 2 times 1 minus 3. 1 minus 2 minus 3. Negative 4. Calculate g of 2. I have a 2 squared minus 2 times 2 minus 3. 2 squared is 4. Negative 2 times 2 is a negative 4. So those two cancel out, and I just simply end up with a negative 3. Okay. I'm going to go up here, make some room so that I can calculate g of 3. So I have 3 squared minus 2 times 3 minus 3. 3 squared is 9. 2 and 3 give me a 6, and it's negative. Minus 3. Okay, I get 9 minus 6 minus 3, so I end up with 0 again. Okay, now I just simply want to go over to the right and plot my points. And you can see that we have 0 twice in the range. 0 occurs twice for the y, so only way to do that is if this function is curved. And so we drop below the y-axis into the negative y values, and then we come back up to hit the x-axis. Okay, maybe I should have said we drop below the x-axis here. Alright, so I have to erase some of this stuff here so that I'll have room in my graph. At this point, I plot the pairs like I did before. There's one pair, there's another pair of coordinates. So starting with negative 2, I go to the left 1, 2. Okay, so somewhere along this vertical line, and then I want a 5, so I actually need to go up for my y coordinate. That's a little bit straighter. 1, 2, 3, 4, 5. Draw a vertical, or I'm sorry, a horizontal dotted line to meet my vertical, and so these two coordinates intersect there, so I plot my point. What about negative 1, 0? Well, I simply shift over 1 to the left from the origin, and since my y coordinate is 0, I don't shift up or down, I stay on the x-axis. For my next point, I'm at the origin again. I start at x equals 0. I don't shift left or right. I stay on the y-axis, and I simply go down 1, 2, 3, because it's a negative 3. And I plot a point. Okay, at this point you may be thinking, hey, this could be a straight line. But let's plot the next pair of numbers, 1 and negative 4. So I move over to the right one, and this time I go down 1, 2, 3, 4. And now you start to see us break away from this straight path. The next point, 2, negative 3. Here's x equals 2, and now I'm starting to move back up 1, 2, 3, and I'm level with this previous point I plotted on the y-axis. Okay, the coordinates of this point once again are 2, negative 3. Okay, and my last point, I have, of course you could always plot more input-output values for your table. This is my last one. I have 3, 0, 1, 2, 3 on the x-axis, and my y-coordinate 0, so I don't shift off of the x-axis. Okay, if we connect these dots, then you see that we simply form sort of a U-shape, which is characteristic of a parabola. Okay, parabolas can open up or they can open down, and of course they can shift left and right, and they can shift up and down. Page 12. Finding the domain and range of a continuous function graphically. Okay, so when we're reading values from a graph, we're just simply going to read them as accurately as we can. We're not going to split hairs as to whether it lands actually on one of the tick marks or maybe just left or just right. We're going to do our best. Okay, and another thing that's important when you interpret graphs with respect to domain and range are the end symbols. Should you have a curve that does come to an end, and so with these ends that were given in the workbook, might not be obvious, but there's two types of ends that you can have: a solid dot and an open dot. I am going to clear up the confusion and just simply say this is a solid dot, and this other one I'm going to call an open dot. May or may not be obvious to some people, but it does make a difference. Okay, domain. Domain simply refers to our x-axis, and so if you were to picture say a light up above the curve shining down on the curve, and then say you pictured one below, okay, shining up towards the graph, then you could probably say that this curve would cast a shadow on the x-axis. And if you said that the rays didn't shoot out at an angle, we just shine the light directly in the vertical direction, then we would only shade this area of the x-axis. This would be the only location of the shadow. Okay. And so that shadow is going to have limits, okay, on the left and on the right. If you look at this point, okay, the shadow doesn't extend beyond this point here. Okay, this would be the location of the beginning of our domain. Alright, so just sort of a simplistic way of looking at it. I need to read this value of x, so I'm going to go back in here and erase this so I can see the tick marks. And so I just simply start counting, and each unit represents one. Alright, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I'm going to say this point hits 12. Okay. Now, this is a solid dot, and so 12 is definitely in the domain. If I input 12, then I get a number out for y. I get a real number back. Okay, the solid dot indicates that 12 is in the domain, and if you're using interval notation to represent the domain, then we would use a bracket on the side of the negative 12. Okay. Now, so once again, referring back to my shadow, it would extend all the way across the x-axis until we got to the far right at this end point. Okay. So if I simply draw a vertical line from this point down to my x-axis, I will get the limit of my domain. Okay, so I want to count these tick marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I went to the right, it's a positive 14. But now 14 itself isn't included. Okay, and I just simply know that because I'm calling this an open dot. I can pick any number right up until 14. For instance, 13.98765, 13.99999. Okay, and if I use that number for an input, then I would get an output on my y. So let's say that this is x equals 13.9. I could draw a vertical line at 13.9, and I would intersect my function. Okay, but if I use 14 exactly, I pass through this open dot. I don't actually hit my function. Okay, but we use the 14 in the interval notation, and to indicate that 14 isn't exactly in my domain, I use a parentheses. Okay, now I have to do my range. Alright, so with the domain, I sort of use the analogy of casting a shadow. Perhaps I should use these incandescent light bulbs. Okay, it would send out perfectly horizontal light rays from both sides. Okay, that's definitely not straight, but okay, light rays coming out perfectly horizontal. This particular one hits the function and gets blocked, so it wouldn't hit the y-axis. Okay, so in other words, all of the light rays beyond the edge or the very bottom of this curve would pass and would light up the y-axis. And so in other words, I would get a shadow cast along this area of the y-axis. Okay, so if the shadow analogy does nothing for you, then just simply ignore it. Okay, but if I want to fill out the range, the interval notation of it, I need to read this y value, and I need to read that y value. Okay, and I would simply go over here, and these would be the limits of my output, my range. Okay, and once again, this represents a solid dot, and this represents an open dot. This solid dot is actually one of the far limits of the range. However, this open dot is not. Okay, but this value would actually be included in the range because this value pops up over here in this location. Okay, so I don't actually have a gap in the range because of this open dot. Now, and this open dot is not the lowest or the highest point on my function. That happens here. This is the lowest point. This part of the curve is my lowest point, and so I want to actually find the y coordinate of that and use it as one of my limits in my interval. Now, when we actually have a part of the curve create one of the limits of our range or domain, we are going to use a solid dot, or a bracket, in other words, to represent that coordinate. Brackets. Okay, brackets to represent parts of the curve. So I'm going to go back and erase my shadow so that I can read these tick marks and get accurate coordinates. Okay, I always start with the smallest and end with the largest value for domain or range. So for the range, I'd count down from the origin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. Hopefully I counted that accurately. I am just going to simply call it negative 13 because I counted down from the origin. And again, I'm going to use a bracket in my interval notation because negative 13 represents a piece of my curve. Okay, now I need to find the coordinates for y2, the upper limit of my range. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, positive 10, and that was a solid dot, and so that would be assigned a bracket as well. So in other words, what I'm saying here is that the only output values that I can have for this function are between negative 13 and 10, and they include those numbers themselves, negative 13 and 10. Okay, for my domain, I think I got negative 12 and 14. Okay, so these are the only inputs that I can use and expect to get an output from my range. Alright, so let's take a look at some other functions. Okay, once again we're given a graph and we want to read the domain and the range. Okay, I'll call this an open dot this time, and I'll say that this is a solid dot. Alright, you should be able to see that these dots on this curve represent the farthest to the left that I can go and the farthest to the right, the extremes of my x values. So for the domain, with this being an open dot, to me that looks like it falls right between negative 4 and negative 6. I'm going to call it a negative 5. And since this is an open dot, I would use a parentheses. Okay, and if I apply the vertical line test anywhere above negative 5, then I most definitely strike the curve. There are no gaps. It's completely continuous in between these two extreme ends. Okay, So what are the coordinates of my solid dot? Well, this one you could argue falls right down in between 2 and 4. So I'm going to call this x equals 3. With x equals 3 having a solid dot, then I'm going to use a bracket for my interval notation. And that would complete my domain. Okay, what about my range? And so when we say range, we are referring to the y-axis. And I'm looking for the highest and the lowest point. Here is the low, and here is my highest. Okay, and you can see that these locations are actually parts of the curve, and we don't actually have solid or open dots. And remember from the previous example that we are going to use brackets for whatever coordinates that we come up with for these points. If I extend this over to my y-axis, I get y equals -4. And then this one hits the y-axis at exactly y equal 4. So my range spans from y equal -4 to 4. In interval notation, I would use brackets. These are the only outputs that I can expect for any particular input. These are the only numbers that I can put into this function and get a real number back. Okay, and if you look and apply the vertical line test at any point along the x-axis, I can only hit it one time. Okay, now here's some other things that we can do with the graphs of functions. This is telling me for what values of x does f of x equal -4, and so this could be translated as y equal -4. So we're not inputting a value for x, we're looking for a particular output, and we want to know what input gives us the -4. So we, in other words, we start with the y-axis this time. So let me remove some of the clutter from my graph. And once again, I go over to my y-axis. I find y equals -4. I draw a horizontal line over to my function f of x, and I would strike the curve right there. And from that point, I want to head in the vertical direction until I reach my x-axis, and at that point I just simply read the coordinates that I hit. Okay, I'm going to say I hit x equal -2. Okay, and remember, for a particular output, we can have several inputs with that same output. So you don't want to just simply head in one direction all the time. Okay, if there had been an area of the curve that was down on this side, then I would have went to the right and went up towards my x-axis. But this is the only point located down along the horizontal line, y equal -4. Okay, let me do another example that is not in the workbook. Say for instance I had an f of x equal, let's say, -2. Okay, similar to this example but with a -2. I would go to my y-axis. I would locate all the points along my function that fall on this horizontal line at y equals -2. And it turns out there are actually 2 points. So I have to find the x value for each one. I go up from this one. This one looks like I fall right between -2 and 4, so x equals -3. And my other one, just to the right of -2, so I will call that -1.9. So in other words, if I calculate or read from my graph f of -1.9, I will get -2. If instead I use -3, f of -3, I will once again read -2 for my y coordinate. Okay, now we're given one, just the algebraic expression of this function capital F, and we want to come up with the domain and range. To do this, I need to bring up my graphing calculator. Okay, so here we go. I want to graph this function x to the fourth minus 12x squared plus 4. And I need to go back and correct this because I need a -12 in front of my x. I'll hit second and INS, and that will allow me to insert a 12. And now I'll simply arrow over and finish it up with a +4. Okay, now we get into the game of find the function, and that can be difficult sometimes. But in this case, if you look at our function, it's actually a polynomial, and our highest exponent is 4. Little trade secret when analyzing functions is that if our degree is 4, then a lot of times our function can simply look like a W. Okay, and you kind of see that here on our calculator. You just can't see the bottoms of the curve. So I'm going to have to zoom out. Alright, and so it zoomed out. It sort of scrunched up our function in the middle of the screen. I'll now go back to zoom box and try to get a better picture. I really just want to get the bottom, or in other words, the lowest point of my f function. Okay, here we go. Now we can see the absolute bottom. One way to check the coordinates, and again, I want to find the coordinates of these 2 points, and I want to pick the lowest one. That is going to be the beginning of my range. Okay. A precise way to do that, have your calculator give you good, accurate coordinates, is to use the calculate menu. So I simply hit second and trace, and you see the in blue letters CALC for calculate brings up this menu, and I want to find the minimum of this curve. it prompts me to go to the left of the particular point that I'm interested in. This is the point that I'm going to do first, so I go to the left and I hit enter. And now it says right bound. I go to the right and I hit enter again, and then it prompts me to guess, and I just simply hit enter again. And you see that it gives us the coordinate x equals negative 2.44. That's the x coordinate, but since we're filling out the range, we're interested in the y, and I get negative 32. If you follow the same procedure for this other point, you should find that its y coordinate is also negative 32. So these 2 points are going to represent the lowest value of our range. So I will go here and I will put a bracket, since I'm referring to a point on the actual curve, right in negative 32. Now, what are the upper limits? Well, you can zoom around and you can look for it, but you'll never find it, because the upper limit of this function is infinity. In other words, if I continue to put in very big numbers for x, I will always get a bigger number back. Okay, I'll always get a larger output for a larger input. That's sort of my way of saying that this function f does not have an absolute maximum. It continues out to infinity along the y-axis. Okay, and that's pretty much what we have to argue in terms of the domain. You can pick as small a number or as large a number as you want to, insert it into f of x, and you will always get a number back. Okay, and this sort of goes along with what we were talking about earlier with polynomials. If you look at the expression itself, you see that all of the exponents of the variables are positive and they are whole. Okay, we don't have those two restrictive cases that we mentioned earlier, such as the radical or an x variable in the domain of a fraction. Okay, so in other words, we can insert any number in for x. The domain is all real numbers. Okay, let's continue to the next example. Here we're sort of switching gears and we're talking about the intercepts. A lot easier to think about with respect to the domain and range. Domain and range are probably one of the most difficult questions students can be asked in college algebra. Okay, intercepts, not the case. Okay, the rule is simple. If we want to find the y-intercept, or simply the location where we cross the y-axis, then we set x equal to 0. If, on the other hand, we want to find the x-intercept, or in other words, the zeros, then we do the opposite. We set y equal to 0, and this one's a little more difficult because we have to actually solve an equation. Whereas if we put in 0 for x, we're just simply calculating or evaluating an expression. Okay, so example 5 just simply wants us to do this first one, find the y-intercepts. Okay, this is the linear function that we had before. I want to find the y-intercept, so I put x equal to 0. That piece drops out. 0 times 3 is 0. And I get a negative 1. The coordinates for my y-intercept are 0 and -1. What about g? Well, again, I insert 0 for x, and I just simply calculate. These terms drop out, and I'm only left with a -3. So the coordinates of my y-intercept, if I were to graph g of x on my calculator, the curve would cross the y-axis at 0, because it's the y-axis, -3. Very simple finding the y-intercept. Okay, on the next page we're given a picture or a plot of a function. And we're told this time that we want to find both the x-intercepts and the y-intercepts. Here are the x-intercepts. Maybe I could extend this. And you can see that there's 3. And this time I'm not given an algebraic expression for my function. I just simply have to read these coordinates. So for my x-intercepts, and if you'll notice, any point along the x-axis has the y-coordinate of 0. We're located at 0, or the origin, y equals 0 on the x-axis. So all of these coordinates are going to have a 0 in the second slot of the ordered pair. Alright, 1, 2, 3, 4, 5. -5 is my first x-intercept. My second one, 1, 2, 3, 4 is my other x-intercept, and then the last one, 4, 5, 6, 7, 8, 9, 10. So 3 x-intercepts. Now, I want to find the y-intercept. Where does this curve cross the y-axis? Well, it only does it in one place. For the input value of 0, if this is a function, I can only have only one output, one y value. So I just simply want to read these coordinates. And of course x is 0. I'm on the y-axis. 1, 2, 3, 4, 5, 6. Looks like 6.5, and I'm up above the x-axis, so that's a positive 6.5. This is the only y-intercept that I have for this curve. Okay, so this section of the workbook is somewhat long, and I may actually be going a little bit slow, but I'm probably going to break this section up into 2 videos, but before I finish this one, I will finish this last example, example 7. Okay, this tells me find without a calculator the x and y intercepts. So again, I just simply insert x into my expression. And I calculate. So 0, -1 would be my y-intercept. G of x, insert 0 for y-intercept. 0 squared 0, -2 times 0 is 0, and I'm left with a -3. 0, -3 are the coordinates of my y-intercept. Now, the tricky one, x-intercept. Y equals 0, or in other words, you can simply take the function notation f of x and g of x and replace them with zeros. Doing that for f, I get 3x minus 1 equals 0, and so now I have this equation that I have to solve for x. This one's pretty simple. I just get the x by itself, add 1 to both sides, divide by 3, and I get x equals 1/3. So the coordinates would be 1/3 and 0. This would be the x-intercept of f. Now the next one would be a bit tricky because this would result in a quadratic equation. However, it's already in standard form, meaning that I have 0 on one side, all the terms on the left. With this squared term, I have to factor, or I have to apply the quadratic formula. In this case, x squared minus 2x minus 3 is factorable. I'm going to write this as a polynomial times a polynomial. X times x would give me my x squared. And now I want to find two numbers that would multiply to give me a -3 and add to give me a -2. And there's only two pairs of numbers where that will work, -3 and +1. Okay, so these are my two factors, and I just simply split this up into two easier equations. I would get an x minus 3 equals 0, and I'd get an x plus 1 equals 0. Add 3 to both sides. There's one of my x-intercepts. Subtract 1 from both sides. Here is another. And so in this case I have two x-intercepts, and their coordinates are 3, 0, and -1, 0.